let's discuss the two labs, the A and the B. First off, A, which was with a bar magnet. One side of the bar magnet marked north, one part marked south. And then you move the compass around that. What general shape did, how can you describe the shape of the magnetic field around that?
It was towards or away from it.
Okay, let's be more specific. Was it towards or away from it?
It was towards the south and away from the north.
Towards the south and away from the north. And we could see that based on our compass needle. So we can use that compass. The compass itself is just a little tiny, tiny magnet that's going to align itself with nearby magnetic fields, or even very far away magnetic fields in the case of the Earth. What about in the middle then?
In the middle, it pointed straight. It pointed towards the south, but just straight.
Kind of straight, like this, sort of like so, right?
Yeah.
And away from the north again.
Yeah.
And away from the north and towards the south. And in fact, if we were really diligent, or if we took some of the iron filings and shook them out, we'd see that these actually connect. Yeah, the printer's going. But yes, they're always going away from the north and towards the south. But what does that mean? Your compass pointed away from the North Pole? Where does it usually point?
Technically to the North Pole, but technically to the south.
What do you mean by that?
It aligns itself to magnetic north, but magnetic north really is south.
The poles are actually reversed from what you'd normally think of. The reason for that, and that's why our compass points away from magnetic north and towards magnetic south. That's confusing until you realize that what we call north and south poles are actually shortened names of what people originally called them, which was the north-seeking pole or the south-seeking pole. So when people started playing around with magnets and saw that it would align itself to the Earth's pole and show you generally north, they had no idea what was going on with the magnets. All they said is, this one points north. Let's call it the North Pole. That's all. So this one will align to geographic north. That's the only reason it's called the North Pole. Doesn't really matter which direction it's actually pointing. As it so happens here, the geographic North Pole is quite different from the magnetic North Pole of the Earth. Magnetic North Pole is somewhere in Greenland, I want to say, actually. But I'm not 100% sure. So there's always some change. As it happens here, though, maybe it is in Canada, because it points almost directly true north where we are here. So a compass works very, very well here, but in other parts of the country it would be off by several degrees. Yes, ma'am.
So in Europe, if they're looking for north, they're actually pointing like northeast?
Yeah, they could be 20 degrees off.
Oh.
Don't the magnetic poles move?
And they are moving, too. And in fact, runways on airports are numbered based on their heading and to magnetic north, and some of those have had to have been changed in Florida, I know. Yeah.
So geographic north isn't magnetic, like.
Correct.
So geographic north is magnetic south.
Right. Because the way we named the poles of magnets was this one points north. But when you get two magnets together, the north and south poles are attracting each other. So if one points north, it's actually the opposite pole. It is attracted to the opposite pole.
Oh, okay. So then
We call it the north and south pole of a magnet only because it's the north-seeking pole, the one that points geographically north.
Are we dealing with magnetic north?
We deal with magnetic north and south, yes.
South.
Yeah. So magnetic north, magnetic field lines exit from, and they point towards magnetic south. Yeah.
So when you find, like, say you do follow your compass all the way to magnetic
Where,
north.
I don't know if it would spin or what.
Like,
I'm
what
not
would
sure.
happen?
I'm not sure.
Explode in your hand.
Yeah, Justin.
Okay, so So for a compass, does it point towards magnetic north or magnetic south?
Both, really, right? It aligns itself, and so
Well,
I
right,
think
so
it would.
that's-
I think it would depend on which one you're closer to, how it aligns better. But on the Earth, since the Earth is so big, that's pretty much going to be in a straight line. But it'll follow these curving lines.
So like right now, if it's pointed, like it would point this way, is that magnetic north or?
Magnetic north, yeah. So we're more like here, right?
Okay.
And so it would point technically to magnetic south. Sorry. But that would be close to geographic north.
Right. Because it's there.
Yeah, so we would actually be more up here since we're in the northern hemisphere. That's no good.
When the compass points to magnetic south, then it's pointing north.
Geographically it's north, but magnetically it's south. And that goes back to how we defined what a compass pole was. Yeah.
So what about the like the arrows? But the compass, when you put it in the center of the two sides, it's pointing directly at it. So where would the two
Along the line, right?
where
Okay.
would the two curve arounds go?
Because if you're right in the middle here,
No, on the two ends.
oh, right here?
Yeah.
Oh,
Is it pointing
just
straight
the,
at it?
the closer you are to the center, this will go out, but it'll make a bigger loop back. So it's still pointing almost directly south when you're right there.
Bless you.
And then if we could look inside, it would continue to point that way.
Where would the two curve around?
Very far. I don't have room on my board.
Okay.
It goes farther and farther out. So the Earth's magnetic field, while not real strong, extends really infinitely into space. It just grows weaker the farther away you are. But that's important to us because without that, the charged particles from the sun would come in and scour away our atmosphere. It would just blow it away.
Oh, that's what happened to Mars. That's
Mm-hmm. Yes.
Okay, just to clear things up. Okay, so if we stood here and followed where the compass pointed north, would we end up by Greenland or down on the other side of the world?
Yeah, Greenland or Canada or wherever. That
So
is.
it does point to north.
Yes. That's what I've been saying the entire time.
But it's magnetic south.
But magnetically, that's south. That's the south
Yeah,
magnetic
yeah,
pole.
right. But it does point towards geographic.
Yeah,
Okay.
roughly.
Yeah.
They're close to the same
But
place.
geographic north is magnetic south, so it points towards magnetic south, which is north.
Yeah,
Okay.
because the compass was named as a north-seeking pole.
Stop confusing.
We're good.
But the north pole of one magnet points towards the south pole of another
Yeah.
magnet. Okay, now the other ones,
Well, if you were to
Geographic north is magnetic south.
experiment 2
Spearmint.
was using iron filings to show you some of the magnetic field lines around things. So you saw how it got much denser right around the poles. If we could follow it, if we were really careful and sprinkled it all around a magnet, it would show us the whole field. And there's some nice pictures in the physical science book.
If you get some magnetic field, then it's
Right here, I'll show these briefly up on the video too. I don't know if they'll show up. But you can sprinkle those. So what's often, or what can be done, I'd prefer not to talk over everyone, is if you put a sheet over these magnets and sprinkle the filings very carefully, those filings, the little iron pieces of iron, will also align to the magnetic poles. And so you'll be able to get a nice map around it. The reason for that, and this only occurs with iron and to a lesser extent cobalt and nickel, is that every atom, well, let's actually keep that until after the next one, until we talk about the next lab. Okay. And then the last one, what other phenomenon have you observed that has similar fields? This actually ends up being a lot like electric fields. If you had a positive charge here and a negative charge here, the electric fields radiate away from positive towards negative. So pretty similar. Yeah, Matt.
So, yeah, when we were doing the iron filings things, it was being pulled toward north as well as south.
It aligns with the north and south, yes. We'll talk about that, yes.
So does the magnetic field go through the object? Like,
Yep.
okay.
Yep, it would be a line. That's what the green arrow here is showing. And positive and negative, of course, those are for charges. They don't really relate to magnets. There's no positive. We don't call it positive and negative. Okay, and so we'll keep that. We're going to talk about why iron is magnetic and what it comes from after we talk about the second one. Lab B. So lab B, we had, first part of it was just look at a straight wire. We'll have a straight wire going up with some current either up or down. Let's make it go up. Current is up. And what are the magnetic fields in the plane that's perpendicular to this? So on the picture we had the wire here. And what's happening to the magnetic field around it? What did you see? Yeah? Going counterclockwise when the current is up. So the compass would change its direction little by little as it goes around, so that it was counterclockwise. If you looked at it with the wire here and the current going down, how did that change?
Went clockwise.
Went clockwise, right. So what this was showing is that when you have current, when you have moving charges going through something, you get a magnetic field around it, but it's not a magnetic field like an electric field that radiates out every direction. It actually circles around. This is the first application of what we call the right-hand rule. So this is at the bottom. Take your fingers of the right hand. Put your thumb in the direction of the current. So in this case, the current's going up, which would be out of the paper, or in this case, up the wire. Curl your fingers into a C shape. The thumb becomes the wire with the current. The fingers point in the direction of the magnetic field as it goes around. So if my fingers are behind the current carrying wire, it shows that the direction of the magnetic field behind the wire, so into the wall, would be that way. If I follow it around, if it's beside, it's coming out of the board here. Keep following it around. When my fingers are in front, they're pointing that way, and follow it around into the board. Or, in this case, if the current's coming up out of the paper, my fingers curl around in the counterclockwise direction. If I want to look at it down, so into the paper, the current's going into the paper, magnetic field curls clockwise around it. Yep.
So I'm just wondering, since Troy and I haven't done this lab yet, how come it doesn't point either directly away or directly towards it?
I'm not sure I could answer that without some review of third-year physics. And even after that review, I'm not sure that I could answer it in a way that would be satisfying. The mathematics of it show that the magnetic field is orthogonal. It's perpendicular to the movement of a charge. I don't know that I ever could explain exactly why. I could describe it better at one time, but I don't know that I can answer why. Yep.
So is the strength of the magnetic field the same around the wire?
Yes, in concentric circles. So stronger here than here. So this is weaker, weaker still. Still go opposite direction. Still going the same direction each time, but getting weaker the farther away it is from the wire.
Like atoms.
Atoms don't look like that.
I'm talking about other stuff. But
You're talking about a model of an atom with everything concentric.
Yes.
but which is not actually that accurate. Let's look on the back then, too, because on the back you had current carrying wires, but now these wires were coiled into something we call a solenoid. What did you notice about the magnetic fields in experiment 2A and 2B as it relates to the first experiment that we did with the bar magnets? Yeah? Okay.
Look more like a bar magnet. To look more to the top.
Right. It looks like a bar magnet. Either north or south pole could be different, but it looks like a bar magnet. If you reverse the current, the pole should flip, but still look like a bar magnet, just like you flip that pole. So the bottom part here is an extension of that right-hand rule. So I'm going to bring up quick the bottom part so we can see, I can show you what I mean exactly with that last part of the conclusions.
Spaceship.
Okay, so we're going to extend what we saw with the right-hand rule in the first part of this experiment to now the coiled part. We're just going to look at bit by bit, though. So this first one, if you're looking at the top view, there is a part of the wire that's visible, and then this dashed line is the part that would go underneath the core, and this gray part is the iron core. So it's spiraling around like this. But I just want to look at a tiny bit of the wire at a time as we're getting started. So let's look at the part that would go up like that. And I'm saying the current in this example is going up. Well, if we use a right-hand rule and curl our fingers around, that tells us the direction of the magnetic field around this wire. So the direction of the magnetic field would be like so, with the wire in the center. In the back of this wire, into the board, the magnetic field is going to my left, right? So wire up here, curl it around, magnetic field is to my left. And it would be continuing to go around. If I come out of the board, so towards us, magnetic field would be to my right. If I go to the next one, so the current comes up the wire, it would go back, come up the wire again, I'd see the exact same thing. So that all of the wires inside that core have a magnetic field going that way. On the outside, they have the magnetic field going this way. Over here, it's looking at just the little bit as it's coming straight out of the paper or going straight in. And that looks a lot like our first experiment in this section. So the current flows up out of the page here. So it would be coming up and going in like this, following the coil. Well, up, we know what that looks like. It's coming up out of the paper. Right-hand rule says magnetic field goes around counterclockwise. Same thing for this one because it's still coming up out of the paper. Here, going into the paper at the top of the loop, it's curling curling clockwise. Notice though that both of these, when we get into the core, the top and the bottom both have magnetic fields going that way, inside the core. On the outside of the core, it'd be opposite. So out here and out here, it'd be going the opposite direction. But now zoom out, that's what the bar magnet looked like in the first place. I can't see. That is what our bar magnet towards the top looked like. That it would be coming out of one, I don't know which direction is which, but let's just say it was coming out of one, in, around, and into the other. And then in here, straight through. The other one, if you flip the direction, it's going to go the opposite way. Like so, but still look like a bar magnet. There is a second way that we can use the oh, that's nice. The right-hand rule with this. If you've got a coil of wire, and you can identify what direction the current is going. So let's say the direction is it going from the left-hand side of this to the right-hand side. That would mean the current is going around this way as it wraps through the coils. I put my finger in that direction, and my thumb points in the direction that the magnetic north is. So this one would have north. Magnetic field lines would come out of it, wrap back around into the south. If we flip this around and have current coming in this one and going out here, now magnetic field, or the electricity is going this direction. I wrap my fingers around it. My thumb points in the opposite direction because now the magnet has been flipped. Yes, Caleb?
So your fingers are pointing at the north side for both of them?
In the first one, with just a single wire, up here, my finger, if I've got a single wire, my thumb points in the direction of current. I'll summarize these in a minute. And my fingers curl in the direction of the magnetic field around the wire. In the second application, if we have a coil of wire here, my fingers curl in the direction of the current, and my thumb points in the direction of magnetic north.
So what does, like, when you say your fingers, for the first one, your fingers go in the direction of the magnetic current? Which, like,
So consider a wire like so, and let's assume that current is going that direction. It's a single wire, so I point my thumb in the direction of the current in the wire, curl my fingers, magnetic field would be like this around that wire. Okay? Point your finger, point your thumb.
I get it, I just
Okay.
don't know, like, the magnetic field direction, like, I don't know what that means.
Magnetic field, so that's what we saw in the very first part. Magnetic fields always point away from north and towards south. So magnetic field here is this way. And then it would be curving around. But what the right-hand rule is telling us is the direction of that it would be pointing in the first place. Mm-hmm.
So if like it's going around the coil, the like current or whatever, you know.
Okay. Yep, the current in the coil.
What happens to the like when it's like directly?
What happened? Okay. There is so that I think if I understand you correctly, I'll try and draw it. Let's say here is an iron core. We have got current going like this. So a coil. Yeah, that doesn't work for me. Okay, and let's say that current is going that way. What direction is a magnetic field? Okay, so we're going to take, and this is, I picture it going around the, around it like so. Darn it. Okay, so we can't see part of this because that's the part behind, and I drew that completely wrong. I erased the wrong parts.
Just erase it all.
Okay, current's going. Okay, we're going to draw it like this. So the way I drew in most of the images are like this. So here's our wire, current's coming in this direction. It would be going around like so. Curl your fingers around. This points in the direction of the north pole of the magnet. So this is the south pole. Magnetic fields go from the north to the south. Inside, it's that direction. So what your thumb is pointing is in the direction inside the coil, where is it going? To the right. Yep.
Troy has a question. When you put your thumb, doesn't your thumb point towards the direction of the current's going? That's his question.
In a straight wire, yes.
Yeah. See?
So if we took a single section of this wire, say this section right here, the current is going up, magnetic field goes this way around it. Inside where the core is, it's pointing that direction. So that works too.
So it goes back to this.
Yes, Matt.
So on the outside, it's all going towards south, but on the inside, it's all going toward north.
Right. Yep.
Why?
So,
We can't get there right now. We don't have time.
So
Yeah.
with the straight wire, you point with your thumb towards, or the way that current's going.
Yep.
And then these ones, you with your finger.
Wrap your fingers around the direction the current's going. We will try, remind me, we will summarize that in writing tomorrow, and then we'll discuss where magnetism comes from.
I wasn't asking where it's coming from.
You are, actually.